All right, let's wrap up section 2-3. We'll finally do the last test and we'll put all this stuff together to find all the zeros for a function without a calculator. So the last thing we got to talk about is the boundary test, which is, in my opinion, a really bad name. We came up with the Easter egg test a couple of years ago, and it seems to fit a little bit better. And the reason being, when you were a kid, you might have been going too far from where all the Easter eggs were, and somebody would say, "Oh, you're getting colder, you're getting colder." So it's kind of like that. It's more telling you where you're getting hotter and colder for finding zeros instead of like the actual fence of like, don't go past this point. And something else I will point out to you, you may find a zero that is the last zero out there. You'll never have another, like if we got a 0 at 3 and there's never another one past 3. That's kind of a boundary, but it may not show up as a boundary. I've got an example, I'm going to show you of that later too. So I'm going to probably refer to it as the Easter egg test. If you want to, that's fine. Formally, it is the boundary test. So that's what we'll go with. As far as formal language, so for any polynomial with a positive leading coefficient, and yes, that's important, you do need a positive leading coefficient to make it work, and with a factor x minus c. Now, I need to point out that you got a little freedom here. C doesn't have to be a 0 of the polynomial. As long as it's, you make up any factor, x minus whatever in the world you want to use. It can be irrational if you really want to get crazy like that, but it can be anything. And we can deal with the remainder later when we divide it out. That's something that we're going to keep dividing like we've been doing. So with any factor, this is any factor, not necessarily a factor that leads to a 0, but any factor that you create and want to divide out. So here's the two rules. If C is positive, so now thinking of C as an x coordinate, okay? If that C value is positive, greater than 0, and then you do synthetic division, right? So you're dividing that out just like we've been doing to see if it's a 0. And if you do synthetic division, or you could do long division too, and everything is positive or 0 in that synthetic division result, then C is an upper bound. Okay. It's a lot to take in, I know, and I'm going to explain it and actually prove it here in a moment why that's got to be true. And I think that'll clarify what's going on. So you can look at the rules right now. I think it's best to just kind of look at it, think about it a little bit, but don't spend too much time trying to process it. I think it makes more sense to just dive in and see an example. So the other side of it is looking for a lower bound. So on the left side of the graph, if C is less than 0, so a negative value. All right, then you go through and you divide it out, you do synthetic division, and your result has alternating signs. That C is a lower bound. So in other words, you pick a value for C, like -2 or something. If this is what happens when you do your synthetic division, you don't need to look any further. There will never be another 0 past that point. So let's look at an example, and I'm going to pull it up on Desmos and cheat at the beginning here, because the first thing I'm going to ask you to do is to name an integer upper boundary. And what that means is it's not the cutoff. It's more like hunting Easter eggs. After this point, I would be saying you're getting ice cold. Better come back. So find a point, an integer value that we don't need to go any further. We're never going to find a 0 past that point. So let's take a look at the graph and see what might qualify. So if I'm going to cheat, I'm going to use Desmos 3.04 and some odd change. That's the last positive 0 we're going to have. So I'm going to pick 4 as an integer value and say, you know what, looking at the graph, which I know we're going to get into how to do it without a calculator, but looking at the graph, there's nothing past 4. That's not going to have a boundary past that. So I'm going to go ahead and say 4 for now. It's really so I've got something concrete to do the math with in just a minute. So I'm going to ask you to do it on the other side. Let's find a lower boundary. So on that left side. All right, cheating again. A little bit past -2, so I'm going to go ahead and say -3, guaranteed there's no more zeros past that point. Because the function's going down forever past that point, so you're never going to get another, it's never going to come back up, you're never going to get another 0. And I might as well talk about that now, because when I start proving it, that's really what it comes down to. You get this last place right here. And if we can prove that from this point on forever, the graph is positive or even negative, really, that means it's never coming back down or never going back up if it went this way. That's really what it comes down to. If you can prove that from this point onward, the graph never comes back to the x-axis, it's got to be a cutoff. It's got to be getting colder past that point. So I'm going to say -3. That's going to be my lower boundary. Again, not really, boundary's the name, but it's more like that's kind of, don't go past that. You get an ice cold if you go past -3. So let's prove it here. All right, so let x be 4. That's the upper boundary that I came up with. Okay, and I can pick anything from 4 and greater, and it's going to work. So I'm going to make a little note of that. Let x be greater than 4. So I think 4 is a boundary. So let's let x be anything bigger than 4. And I mean like 4.000001 or something like that. Something very close to 4, but just slightly bigger. All right, let's run through what happens if we do synthetic division. So we put 4 in the box. And we've got 2, -3, -12, and 8. It always helps me to say it out loud. I'm going to double check and see if I got everything right. Feel pretty good about that. All right, so 2 times 4 is 8. And that's going to be 5, multiply is 20, add 8, multiply 32, add, and it's 40. And that's my remainder. All right, so the rule says that if I do synthetic division, I could do long division, but I mean synthetic's way easier. So if I do synthetic division and every one of these terms is positive, then I have found an upper boundary. That's what the rule says. So let's jump back to factor remainder theorem for a second. That means we can define this polynomial as x minus 4 times what's left over from synthetic division, so 2x squared plus 5x plus 8 plus 40 over the thing we divided by. So by factor remainder theorem, that's got to be true. The function can be written as this particular factor times this quotient plus that remainder. That's got to be true. We know that's true. We proved it. So let's think about what happens if x is anything bigger than 4. Because if 4 is an upper bound, anything past that is it's never going to come back down across the x-axis. That's the point. So let's prove that that's going to happen. So this point, I'm not going to really just go pay attention to signs. That's the main thing. So think about the signs you're going to see. So if x is anything bigger than 4, okay, well, anything bigger than 4 minus 4 is positive. I mean, even if it was like 4 point a bunch of zeros and a 1, you've got 0.00, a bunch of zeros and 1, but it's a positive number. So that should hopefully make sense. If I put in anything bigger than 4 right here and subtract 4 from it, I'm definitely going to get a positive number. Guaranteed, no exceptions. Can't go wrong. Now let's run through the same idea. If we take 4, or any number bigger than 4, and you square it, it's positive. And you multiply by positive 2, it's also positive. And if you multiply by 5, it's positive. And if you add 8 to it, it's still positive. And if you put in something bigger than 4 in its denominator, and subtract 4 from it, that's a positive number. And 40 divided by a positive number is also positive. So if you look at what's going on here, you're ending up with a positive times a guaranteed positive. So your f of x, your y value, anywhere bigger than 4 is guaranteed to be positive. So that tells you that for any y value beyond this point, if you start at 4 and you go to the right, every y value from that point on is going to be positive. That's a proof, that's guaranteed. So that means it's never coming back down. It's never going to cross the x-axis again past that point. That's how we know that's what we call boundary. Now let's do the other part. Let's try that lower boundary we thought about. We said -3. Let's plug it in and see what happens. Now I'm just restarting the synthetic division, brand new problem. I'm just going to see what happens with that. If I divide that polynomial by this factor, x, the x plus 3 is a factor, but -3 is what goes in the box. Okay, so we've got signs that are alternating, and that's what the rule says, tells us that's a lower boundary. So let's prove why that has to be the case. So let x be anything less than -3. I'm conjecturing that negative 3 is my boundary. So let's let x be anything past that point. If I can prove that the y value will never change past that point, it'll always be negative or positive, that means the graph never comes back to the x-axis, whichever way it goes. You'll never have another 0 past that point. That's what the test is telling us. So by factor remainder theorem, I'm going to come down here so I've got a little more room. Your function can be written as x plus 3, because it's x minus that factor, and times 2x squared minus 9x plus 15 minus 37 over the factor x plus 3. And that would be, again, by factor remainder theorem, our function is equal to this factor times this quotient plus that remainder, which happens to be negative, that's why it's minus. Okay, thinking about signs again. So let x be anything less than negative 3. If you add 3 to that, you still have a negative number, guaranteed. Try anything you want, I promise, it'll be negative. In here, all right, you take anything that's negative, less than negative 3, so a negative number, and square it, it's positive. Multiply by 2, it's positive. Take any negative number, multiply by negative 9, it's going to be positive. 15 is positive. Now, put in anything less than negative 3 here, add 3 to it, it's still negative. And negative 37 divided by negative is positive. And what happens when you multiply a negative times a positive number? That's got to be negative. So that tells me that my y value, let me just kind of make that statement, y is negative. So anytime my x value is less than negative 3, my y value is guaranteed to be negative, which really doesn't matter if it's positive or negative. What matters is that it will never change sign, so that function's going down forever. It's never coming back up and crossing the x-axis. All right, this is what it's all coming down to. This is kind of your final test to see if you understand all these rules. Now it's time to take a polynomial and find all of the zeros with no calculator. So where I would recommend we begin is our rational zero test. Let's take a look at what the possible zeros are, at least the ones that are rational numbers. And then we'll try to narrow down that list. Ultimately, there's going to be a lot of guess and checking going on here. These may take a while. I mean, here, I'm going to be up front with you. You might luck out and find a zero right away, and then things will run really quick. The hardest part is finding one of your zeros, finding your first one. All right, so if you spend 5 minutes looking and you haven't found one yet, and you want to get the calculator out for your homework and find one of them and then go from there, that's probably a good practice. All right, try to find them without a calculator, but if it's really taking a long time, I don't want you getting frustrated and bogged down on just looking for a zero, because I know y'all can handle that part. But I just want you to understand, I want you to know how to use all of these tests together to find all your zeros. That's what it comes down to. So let's look at our possible rational zeros. All right, well it could be factors of plus and minus 2. So let's do it this way. It's plus or minus 1 or 2, factors that make 2. And plus or minus factors that make 6. So 1, 2, 3, and 6. All right, and that's not a very good way to leave it, so let's do this. I'll put it in parentheses, plus or minus. We don't have to write everything twice. But we could have 1 over 1. We could have 1/2. We could have 1/3. We could have 1/6. We could have 2. We could have 2 over 2, which is 1. We already got that. 2/3. And that should do it, because 2 over 6 is 1/3. We've already got that. So at least we've narrowed it down. We've got 6 possibilities plus the negative version, so 12 possibilities. So I'd really rather narrow this list down even more if I can and not have to do 12 different synthetic divisions, because that's really where it gets to. Is now we plug these in for synthetic division and see if we're onto something. Okay. All right. So the next thing I would do is Descartes' rule. So let's run through Descartes' rule and look for positive zeros and negative zeros. at least the possibilities. You're not going to know for sure, but it gives you the possibilities. So I'm looking for sign changes in the original function. That tells me my possible positive zeros. So plus, plus, I changed to minus, that's one change. Stayed minus, went back to positive, that's two changes. So we could have two or no positive zeros, that's possible. It's kind of, if you get an odd number of sign changes, it's kind of nice because you know you at least have one.
Ms. Hinkle, please call extension 3122. Ms. Hinkle, please call extension 3122.
If you get an odd number of sign changes, it's kind of nice because then you at least know you got at least one zero that fits that description. When you get an even number, it's possible you have there's no real positive zero. There's possible they're all complex or irrational, and they're not going to show up this way. All right, now if we do f of negative x, I mean, really all that's going to happen is our odd powers will change signs. So even powers will stay the same, odd powers will change signs. And at that point, I'll put my x in there. Positive to negative, that's one change. Back to positive, so two changes. So also 2 or 0. All right, so that didn't tell me a whole lot. It would have been really nice if this was like 3 or 1, because then I know right away, all right, let's dig in on the negative side and start looking. But that didn't happen. So I'm going to go ahead and just for the sake of doing this example with you, save some time. I already know where the zeros are going to be because I've cheated. But I'm going to pick one right away that I know is definitely going to work so I can show you the process. But basically from here, if you know for sure you've got a positive or negative 0, and then you start looking at your positive possibilities or your negative possibilities. It kind of narrows it down that way. So I still feel like there's a pretty good chance here. I might have two positives, 2 negatives. While you're doing this, the boundary test is not something you just do on its own. While you're searching for your zeros, you're doing synthetic division anyway, check your result and see if you stumbled on a boundary. And then that way you can start crossing stuff off the list. Like if I knew that 1/2 was a boundary, I can start crossing off all kinds of stuff because that's, well, let's see, I've got 1, 2, and 2/3 are all bigger. So then that narrows my list down to these 3. So that's what you look for. If you try something and it doesn't work, but it's boundary, there's no zeros past that point, and you can start crossing stuff off that list, and you don't have to try as many things. It narrows it down for you. All right, so again, I'm going to cheat. I'm going to pick something I know is going to work. I'm going to pick -2. And that's just to save time so you can see the process. So 613, -2. And -7 and +2. So again, factor remainder here. I've got something that I'm going to check to see if it's a possible 0. So I'm going to divide it out. And if my remainder ends up being 0, because the remainder is the y value, then the x I plugged in is on the x-axis, so that's definitely a solution, or 0, or root. That's the plan. So this is actually, I know it's going to work, but doing your homework, you won't always know if it's going to work till you try it. Unfortunately, that's the tricky part. All right, so that checked out. The remainder is 0, so this is definitely a factor of the polynomial. It's a 0 of the polynomial. All right, so what I'm going to do next is try another 0 and see what happens. But something to think about here, I found a -0. So there's definitely going to be a second one. So that's kind of a good sign. That tells me keep looking. There's definitely another one for sure. A couple things to point out at this point. So I like to, kind of in the beginning, should have done this right away. I make a little place to start putting some answers so I'm feeling pretty good about this. Well, how many zeros do we have? Okay, you should remember somewhere back in Algebra 4 or Algebra 2 that you've got 4 zeros because you have a 4th degree polynomial. All right, we will prove that eventually with that fundamental theorem, why that's the case. But for now, take it on faith. I promise there's 4 zeros. Definitely, that's not possibilities. There's definitely 4 zeros. One of them is -2. And we know that because when we divided it out, the remainder was 0. All right, so I'm going to try, I know what the other one is, but I'm going to try something that that maybe is not going to work, and see if we can maybe think about that boundary test. Before I do that, I guess we should check and see if this was a boundary. And it looks like this was negative, so if the signs alternate all the way down, it's a boundary, but that's not happening. So it looks like there's a possibility there's maybe another solution that's less than -2. Now if you think about this though, -2 would have been the furthest thing that way that we could even check on this list. So back to a point I brought up at the beginning. Again, boundary test, I don't like the name because that's the -2 is the biggest thing or furthest thing back to the left it could have been. And it didn't show up as a boundary, by the boundary test. It has to be a boundary. I mean, there can't be any more zeros past that point. So the name, you know, that's why I like that Easter egg name better. All right. So I mentioned trying something that didn't work that maybe wasn't a boundary, but I'm gonna go ahead and level with you. The next thing is -1, and everything else is less than that. So there's really nothing I can check that would show up as a boundary here. So I'm just gonna keep rolling. The next logical thing I would recommend to you is to try your integers. So 2 work, negative, or at least -2 work. So I would just naturally try 1 next anyway because it's just easier. And I think most of you'll do that because why throw a fraction in here if you got integers left that you could try? And then a lot of times you'll find one of those integers is a boundary, and then you can cross things off your list. All right. Now the other thing, we've divided this out now. We've divided this factor out. So I can roll with this quotient and just break it down. In fact, that's what I pretty much have to do. We don't want to go back to the original polynomial. We'll be looking for zeros forever. You take the remaining factors, make the quotient. So let's take that and see if we can divide another factor out. And after this step, we'll be able to factor, hopefully. So 6 comes down, 6 times -1, -5, 5, 1, -1. And that turned out to be a solution because the remainder was 0. And it is showing up as a boundary. Now I take it back. Now let's look at, is this a boundary? Now we've kind of talked about it anyway, but suppose you tried this first. Signs are alternating, but then you get 0 there and it's not really positive or negative. So it's kind of be careful with that. Your boundary test really works for things that are not zeros. That's probably the best thing to think about. If it is a 0, don't even worry about the boundary test. Only worry about it if it's not a 0. So now I've got something that's a trinomial, so I'm going to factor this. This is 6x squared minus 5x plus 1. So I'm going to break out the little shortcut thing. 6 times 1, -5. All right, the two things that multiply to make 6, add to make -5 would be -2 and -3. Don't forget to divide by the 6 out front. If you don't like the shortcut, that's fine. It's probably smarter to use the break the middle term up, do grouping, all that stuff anyway. But if you like the shortcut, I don't want you getting bogged down. This problem's long enough. I don't want you getting bogged down by something trivial like how to factor if you're good at factoring already. So there we go. There's our other two factors. So my other solution, if x minus 3, or I'm sorry, x minus 1/3 is 0, and x minus 1/2 is 0, then 1/3 is a solution, and 1/2 is another solution. So if I was doing this on paper, I'd probably come up here at a proud moment and put all 4 of these in here. I always like to complete that chart. I mean, I feel like I was finishing it up. So -1 worked, 1/3 works, and 1/2 works. Those are our 4 solutions. We found them all. So, whew. So just a quick recap. Begin with all of your possible zeros, possible rational zeros, sorry. And that's by taking factors of your last term divided by factors of your first term. Get your list made. Next, try Descartes' rule. So look for any clues about how many positive or negative zeros you're guaranteed to have. And then don't immediately jump into trying to find boundaries. Look for those as they come up naturally, but don't start seeking the boundaries out. That's not really a good way to go. You could do it, but I wouldn't recommend it. Just start at that point trying. I would recommend your integer values. And if we've got a bunch of integers, let's say it was like 1, 2, 3, 6, 12 on this list, pick something kind of in the middle. And if it's a boundary, then you can cross a lot of things off. That's kind of the general strategy to try. So good luck. Be patient. These will take time. But the more you do this, the more you're going to understand about how polynomials work. And that's what it's all about.